Wade.
Hey, Carly.
So today we are actually going to talk about looking at two variables at the same time.
Oh, interesting. We haven't done this much.
Yeah, so in this series we've talked a lot about variables that are either random variables or just a list of numbers. And we've looked at them through things like histograms. We've also looked at box plots. And now we're going to kind of move past that and think about how can we use one variable to predict another. And the best way to visualize this is through a classic scatter plot. So let's just say I have two variables. Usually we call them X and Y. And I'm going to use just an example of height and weight. And so I have an XY axis, I have weight on the Y axis. This is my Y variable or my dependent variable, and then height is on my X axis. That is my independent variable. And we can use a scatter plot to visually display both of these data sets at once. So generally with height and weight, we usually see a pattern of points that kind of slopes up and to the right, something like this. And if we look at this, we may want to describe this relationship. So I can see that each of these individual points represents a person. So it represents an XY pair. So for example, if I thought about myself, maybe I'd be this person. I could see exactly what my height is if I look down at the X-axis and exactly what my weight is if I looked at the Y-axis. And there's a statistic called the correlation coefficient that can actually measure the strength of the linear association between X and Y.
Interesting. What do you call this?
So we call this the correlation coefficient. And I am going to that's not how you spell it. Correlation coefficient. And I'm going to actually represent this with the little letter R, which is kind of strange because it starts with a C, but in statistics we use R to mean the correlation coefficient.
And we do the same thing in computer science and data science too.
Good to know. So the correlation coefficient, like I said, measures the strength of the linear relationship between X and Y. And it actually ranges from -1 to 1. Which is really nice for interpretability. And it can be negative, it can be 0, or it can be positive. And if the correlation is positive, that means we see something like weight and height. Our points slope up and to the right. In general, as the X variable increases, so does the Y variable. Now, sure, there could be outliers. There could be someone maybe who is really tall and has a really small weight. That would be considered an outlier. And the correlation coefficient takes into account all these points and gives us the statistic between -1 and 1. So if R is 1, between 0 and 1, that means we have a positive correlation. If R is 0, so if R is 0, that means we have no correlation. So that means there is no linear relationship between our X and Y variable, and we just kind of see a blob of points. We don't see points with a nice slope that we could draw a line through. So we have no correlation. I said if R is greater than 0, we have a positive correlation. And then if R is less than 0, we can have a negative correlation. Which all that means is that instead of our points sloping up and to the right, like for weight and height, our points actually slope down and to the right. So something like this.
So as X goes up, Y goes down.
Exactly. As one variable goes up, the other one goes down. And this relationship between our X and Y variable is going to be super useful. A lot of times the correlation coefficient is included in our basic exploratory data analysis to see if there's any relationships between the variables in our data set. And as we move further along in this series, we're going to do some really cool things with X and Y variables and the correlation coefficient, and even use X to predict Y.